Now we're going to get started with elimination reactions. So again, remember this is a continuation of the substitution reactions, which we have already done, SN1, SN2, and now we are in the elimination reactions part. Okay, so remember all the things we have learned in there, we're going to use here also. So first of all, what is an elimination reaction? An elimination reaction is when you eliminate something. When you eliminate something, you end up getting a double bond. Okay, so let's see what we are eliminating. So here you have your substrate as usual, which has a leaving group. And you also have a hydrogen next to that carbon that has the leaving group. And then the base comes in, picks up a proton, okay, and then that leaves along with the leaving group. All right, so a few things to talk about here. So first of all, why is elimination taking place? Elimination is taking place because you're going to treat the substrate with a strong base. What does the strong base do? The strong base is going to go for the proton. Once the proton leaves its electrons on this carbon, the carbon alpha and the carbon beta, then there are going to be too many electrons here, and so the leaving group has to go away. Okay, so do we need a leaving group? Yes, we do need a leaving group, because without the leaving group you don't have any elimination reaction. There are going to be reactions in future that we do in which there is no there is no leaving group, so which means the base just picks up a proton and the proton then just leaves its electrons on the carbon. But then that's not an elimination reaction. Okay, that's just a different type of reaction. That's an acid-base reaction. So in the elimination reaction, you have a leaving group. Now, if you're wondering why does the leaving group go away, it goes away first of all because there are excess of electrons here. And also remember, this carbon and halide bond, or the leaving group bond, is the weak one. Okay, so that has to break. Some other things over here to talk about before I get into more E1, E2 is the fact that these kind of elimination, these are known as alpha beta eliminations. So alpha is the carbon that has the leaving group, beta is the carbon that has the hydrogen. Okay, these are also called 1,2 elimination. Again, one carbon is the one that has the leaving group. Okay, carbon number 1. So 1,2 elimination or alpha beta elimination, however you want to look at it, but these are elimination reactions. So again, what's going on here is that you have a base picking up a proton, which is leaving its electrons then on the carbon-carbon bond, and then the bromine is leaving as well. Then you get a product as an alkene, because when you eliminate something, you get an alkene, and you also have the leaving group gone away. Okay. There are going to be two kinds of mechanisms that we do, E1, E2, as usual, as we've done with SN1, SN2. So, that's what elimination reactions are. The first thing you have to do for any elimination reaction is to identify the hydrogens that are going to go away. Okay, because this has been, I have found, in my classes, that is a little bit of a challenging thing sometimes. Okay, is which hydrogen to eliminate. So remember, all eliminations are alpha beta, okay, or 1,2 eliminations. The problem is not that you don't know that you have a beta hydrogen, is that you forget you can have more than one beta hydrogen, okay, to remove. So below this problem that I have here for you, it just shows you how many beta hydrogens you can have, okay, because when you do elimination, you can remove any of the beta hydrogens, okay, all of them can be removed and all of them can give you product. Now, how many products you get, that's a different thing, okay, because that depends on stability. But you have to know that you can have more than one hydrogen to eliminate. So here I've given you 3 compounds, okay, and if you look at them, they look straightforward enough. Identify the leaving group, and the leaving group is the heteroatom. So here is the heteroatom, here is the heteroatom. And then what you should do to identify the beta protons is just look at the carbon over and see if there are any hydrogens there. So I've marked all the hydrogens here with red for the ones that are to be eliminated. Okay, so the one that you would forget in this case is this hydrogen. Okay, so it's kind of invisible. I mean, it is invisible. You can't see it, right? So it's you forget it's there, and so you don't write it, and so you miss out on one product. Okay, so that's all you have to do is look at the carbon that has the leaving group, and then the next carbon over, the next carbon over, and the next carbon over, see what kind of protons you have available. If you have any protons available, sometimes there is none, okay? And so if you don't have any, that's fine, all right? But go ahead and identify those. So it's an important thing to identify the hydrogens that can be eliminated. So again, look at these, let me know if you have any issues, but that's all you're looking for in this case. So the first mechanism we'll talk about is the E2 mechanism. And remember, what means by E2 is the fact that both the substrate and the base, okay, are going to be involved in the transition state because it's a second order reaction. Okay, so E2 means second order. So in this case, both the substrate and the base are involved in the intermediate. Your product is an alkene, okay? Right now, I'm not challenging you with any kind of number of products. It's just a simple product here, propene. That's it, okay? So how is this working as a second order reaction? So right here, I've shown you the mechanism. So you draw out the carbons that are involved in the reactions. You don't have to draw this CH3 out because it's not involved. So draw the two carbons, alpha beta carbon. So here is the chlorine, here is the hydrogen. So since everything is happening at the same time, why? Because this is a second order. So it means that the base as well as the substrate are involved in the transition state. This is what the transition state looks like, where the base is picking up a proton. So the bond is forming here. The bond is breaking here, the bond is forming here, and the bond is breaking here between the leaving group and the carbon. Okay, so lots of bond formation and breaking going on in this transition state, and then eventually you end up with the double bond, and then here is the base that has picked up a proton, and then here is the leaving group. Okay, and if you're wondering, this is just a Cl minus, what happens? Well, you know that there is always going to be a what do you call a counter ion? Okay, somewhere there's going to be a counter ion, and if it's bothering you that I have Br here and Cl here, I'll change that to Cl. Okay, so that way you don't have to get confused. So for right now, I'm just going to go ahead and write Cl minus, and this is Cl. Okay, so I will change that in the PowerPoint. Okay, so that is your E2 mechanism. So nothing much has changed as far as the second order reaction is concerned. Okay, so go ahead and read all this if you need to in order to understand what's going on. Here is the energy diagram. So remember this energy diagram from the SN2 reaction also, because there's only one transition state, so there's only one curve. Just go through this again. It's the same thing as the SN2 diagram that we had. Now for the E1 mechanism is going to be a unimolecular, meaning that it's a first order reaction. So if it's a first order reaction, then only the substrate is needed here, okay? And not that it's always going to be the substrate, but it turns out, and then in this E1 reaction mechanism, the base is not needed, okay? For elimination, only the substrate is needed. So then the substrate is going to be the starting material, and the transition state only has the substrate in it. Okay, so what happened here is that you have the leaving group going away, creating a carbocation. In the transition state, there is the the carbocation, and then a base can come in and pick up a proton. Okay, now if you look at the base here, it's just water, picks up the proton, and you end up getting a double bond over here. Okay, and so I give this also over here as a side product because sometimes when you have E1 mechanisms, and if you have water, you also end up getting solvolysis, which means that you end up also having the base reacting as the nucleophile. Okay, and so sometimes it's a little bit of an issue, but this is something I want you to be aware of. Are you going to be writing this all the time? Maybe, maybe not. Okay, and so, but you just need to be aware that it is possible that in E1 mechanisms you can have some things, okay, in there. So again, it depends on the substrate, it depends on the mechanism you're working on, and the base that you're working with. So if it's a weak base like this, like water, then you can have substitution as well. When we use strong bases, then you may not get a substitution in there. So anyhow, this is the E1 mechanism, and let's see over here. I don't think I have anything else to mention here. Okay, here's the energy diagram for the E1 mechanism. Again, very similar to SN1, where you have two transition states. The higher energy one is, of course, the formation of the carbocation. That's the rate determining step. Once that happens, the second step is a lot easier. Okay. So the most important thing for an elimination reaction is the base, okay? And we talked about substitution reactions. In substitution, you have nucleophiles. When we talk about elimination reactions, we have bases. Why do we have bases? Because in bases, they have the ability to abstract a proton, and that's what we want to do. We want to abstract a proton. We don't want to have a substitution reaction, okay? So we want to do elimination here, and so we need to have a good base. So what are some good bases? A good base is one that does not attack the electrophile. It's going to pick up a proton. Now, some of these bases that I've written over here, like hydroxide, methoxide, ethoxide, these are also good nucleophiles. Okay, so which means it's going to be a challenge for us to figure out whether we are doing substitution or we are going to do elimination. Okay, that's definitely there, which is something we have to address. But this base, for example, the one I've given you here, which is called DBN for short, this is like a very normal kind of a base. I know it doesn't look normal, but anyhow, it's a very common base that can be used just as a base. Okay, so no substitution in this case. So, when you have bases that look like nucleophiles, then how do you decide whether you're going to do substitution or elimination? And those are the things that we have to talk about eventually, not right now, but eventually we're going to talk, because right now I want to focus on the mechanism itself and the products that you get, not so much on the base. Okay, so right now we are presuming that no matter what kind of a base we use, we are going to get elimination, okay, from it. So later we'll discuss how to promote elimination. So first thing I want to talk about in E1, E2 mechanisms is what we call regioselectivity. Okay, regioselectivity meaning that when you have more than one proton, okay, as I was saying, you can have more than one proton because you can have many beta protons, up to 3 beta protons. So if you have 2 beta protons, you're going to get 2 products, okay, from there. Regioselectivity is where is this double bond located? That is the regioselectivity. You can call it region if you want to remember it, but you can have the location as in this case it's terminal, and in this case, in the second case, it is internal, depending on the hydrogen that is picked up. So these two products are obviously not the same. They're constitutional isomers. The first product in which the double bond is terminal, this is called Hofmann product. And then here in which this is internal, this is called Zaitse's product. Now, I want to remind you that in one of the previous presentations, we talked a little bit about the stability of alkenes. And I mentioned there to you that terminal alkenes are not stable. The more substituted an alkene is, the more stable it will be. So which means that the Zaitse's product is more stable. Okay? Always when you're looking at two products, Zaitse's product is going to be more stable. Why is it more stable? Because the alkene is going to be more substituted in these cases. Hofmann product doesn't mean that the alkene is always terminal. It could be less substituted alkene, but a Hofmann product is where the alkene is less stable. That's all it is. Okay, so it has nothing to do with terminal or internal. It's more to do with the stability of the alkene. Okay, the more stable alkene is Zaitse's, the less stable alkene is the Hofmann product. So what I said to you before about identifying the beta protons is for this reason. Okay, because if you have more than one proton, you are going to get more than one product, okay, in there. And we need to identify those, because now what happens then is if you're getting two products, then are they equal? Right? That's the question. So generally, Zaitse's product is going to be the more stable product, and so it's going to be the major product. usually. Well, yeah. Okay, so let's look at the regioselectivity for an E2 mechanism. So here is the secondary halide, and the first thing we do is identify the two protons. And here are the beta protons, you know, H1, H2. I've color coded them so it's easier for you to see what kind of products I'm getting, all right? So here is the base picking up the first proton, which is pink. You know, it gives you this pink, not double bond, but this product. And then here is this other proton, the beta proton, which gives you this alkene. All right, so the base here is just, you know, I've used similar bases for both of them. So here again, this is the less stable alkene, and that's the Hofmann product. This is the more stable alkene. This is going to be the Zaitsev product. Remember always that the major product is going to be always the Zaitsev product, okay, if you have two products. Now, what's happening over here? Are you going to get both the products? And the answer is yes, you will get both the products because it's possible. But what if you want to just get one product? Okay, can you make sure that you just get the one product? So if you just want the major product, what do you do? If you want only the Hofmann product, what do you do? Okay, now what is the important thing over here? The base. All right, the substrate is going to be the same. Now, in some cases, we also change the substrate in order to promote one product versus the other, which you're going to see later on, okay? You know, one thing you have to remember that just because you're learning this doesn't mean this is the only way to make an alkene, all right? This is one of the ways of making an alkene. What we are learning here is a process of thinking that, you know, if you use this kind of a base and if you use this kind of a substrate, you are going to get two products, okay? So don't just think that this is the process that you have to use. If you just wanted the Hofmann product, okay, then you can use another synthesis. You don't have to use this one, okay, because this is a minor product, so you don't have to use this. So what I'm just saying is that this is a process of thinking, okay? Don't think that this is the only way you can make an alkene. So if you want to make only one versus the other, here is your method of doing this, okay? So here I'm going to go ahead and delete this from here because this is not an E1 mechanism. This is an E2 mechanism, so you don't really need the bromine there. So bromine is still on there because in an E2 mechanism, everything is happening at the same time, right? But now what we are going to do is we're going to change the bases, okay? Here I used methoxide as my base to pick up this proton and this proton, right? That's the only thing I have in solution. Now, let's say that I take this substrate and I treat it with this big bulky base, which is the T-butoxide. Okay, so if I'm using T-butoxide, now because this is so big, it's not going to be able to access this internal proton as much. Okay, it will access the pink one, which is the external one, and that's it, it's done. Okay, so not so much for the H2. However, if you have a smaller base, that can access this smaller one. Okay, and it may not want to get this one because it can get it too, okay? But on the other hand, you know, we are a little bit more specific when we choose a bulky base, because a bulky base for sure will not be able to access the blue proton, okay, because it's internal. So which means when you use a bulky proton, bulky base, then your major product is going to be the Hofmann product, okay, and then your Zaitsev product is going to be minor product, okay, and then things are a little bit switched around when you use a smaller base, okay, and if it's not all switched around, that's okay. It means that maybe this is not the way you want to make this kind of an alkene. That's all it is, okay? Remember again, what you're learning here is, you know, what kind of products you can get and what's the mechanism that's working here. Okay. Now let's look at the regioselectivity for E1. Okay, for E2, we saw what happened. Okay, in E1 mechanism, you will still have the same issue, but in E1, you're forming a carbocation, right? When you have a carbocation, again, you identify your beta protons. Okay, now if you think that, there is one more proton and you say, okay, well, there is a proton here also. Well, these two protons are exactly the same. Okay, and that's why I didn't draw the other one out. And so, no need to confuse all of us right now. Okay, so you have two protons that are possible. So here you end up getting, this alkene, okay, from elimination of this proton, and then this alkene, which is the Zaitsev product from the elimination of this blue proton. So you still get two products, okay, but in an even mechanism, invariably the major product is Zaitsev's product, okay? So which means that if you want Zaitsev's product, you may want to choose E1 mechanism. What does it mean choosing an E1 mechanism? E1 mechanism means that formation of a carbocation, okay? What does that mean, formation of a carbocation? It means that you need a tertiary substrate. Okay, so you can see the cascading effect here where, you kind of see what kind of product you need, and then from there on you decide what kind of substrate you will need. So if your goal is to get a Zaitsev's product as a major product, okay, and if it is possible for you, then go ahead and get started with a tertiary halide, because then you know that the tertiary carbocation is going to be the more stable one. As soon as you have that, your product is guaranteed. Okay, and in the case of E2, remember that we talked about how you can get the Hoffman product by using a bulky base. So you can target your synthesis that way, okay, a little bit. And that's the whole point of learning all of these things. How can you make the product you want to make? Okay, now for stereoselectivities. Now stereoselectivity, this is primarily for E2 only. This is not so much for E1 because E2 mechanism is where everything is happening at the same time, right? Because both the base and the substrate are involved in the transition state. In an E1 mechanism, that's not what's happening. Okay, you form the carbocation first. So this stereoselectivity that I'm going to mention to you, it's only for E2, okay, not for E1. So what is this, stereoselectivity kind of a thing? The stereoselectivity here is that when you have a leaving group, okay, on there, the beta proton that's on the next carbon over, whether it's on this carbon or it's on this carbon, that hydrogen and that bromine, the leaving group, should be at 180 angle to each other. Okay, 180 angle means anti. They should be anti to each other. So that's called anti-periplanar. Okay. Periplanar or co-periplanar is when the angle is less than 180. So if they're on the same side or if they're on similar sides, that reaction is not going to happen, which means E2 is not going to happen. Okay, so which means that we need a very specific kind of a substrate which will lead to elimination, because if you don't have the anti-periplanar hydrogen and leaving group, then the reaction is not going to happen. Okay, so let's look at this cyclohexane. This is a cis cyclohexane. Remember the two hydrogens which you cannot see, right? They are there. So this is a hydrogen and then here is the other hydrogen. So looking at this, you cannot tell whether things are in the same plane or not. So you have to convert it into a chair conformation. Once you convert that into a chair conformation and you draw out your bromine, remember I said to you when I was teaching you conformations that you always start with this carbon over here. Now that we are into elimination reactions or even substitution reactions, put your leaving group on that carbon number 1. That will suit you best, okay? So start with that. So put bromine on the top, okay? And then the other groups, then this is the methyl group. The methyl group is on the same side, so which means it's going up. And then here the bromine is going up, so they're both on the same side. Okay, so they're both going up. So then we look at the protons. Now on this carbon you have 2 protons, so that's nothing to worry about, right? But on the carbon that is with the methyl group, you only have 1 hydrogen, and that hydrogen luckily is going down. Okay, so and luckily meaning what? Let me erase all of this so I can show you that luck has to do with the fact that there is a 180-degree angle between the bromine and the leaving group, Okay, and the other carbon which has the two hydrogens anyway, the blue one is the one that's going to leave, not the red one. Okay, because the red one is periplanar, not or co-periplanar. Periplanar is fine. Okay, so the red one is not going to leave. That's why I've colored it red. Okay, the blue one's going to leave, and the pink one can also leave because both of those are at a 180-degree angle. Okay, to each other, and that is how it works with stereoselectivity. Now this was for cyclic compounds. Now if you have aliphatic alkanes, which means straight chain alkanes, then you will have something like this. Okay, when you have a straight chain alkane with a leaving group, then what you need to do is draw a Newman projection. Okay, and with the Newman projection, then you have to see, okay, where is my hydrogen now? So here is the carbon with the bromine right here, and that's this carbon, right? So it has a methyl group, a hydrogen, and a bromine right on there. And this carbon then is attached to this carbon, which has two methyl groups and a hydrogen. So two methyl groups and a hydrogen, right? So those are the groups that we have here. So now if you draw the most stable conformation for this compound, you can see that the hydrogen is not going to be opposite, okay, of the leaving group. That's not a 180 angle. The hydrogens are less than 180. Okay, so which means that for this kind of a compound, you may not get elimination, okay, because the conformation is not supporting it. And why is the conformation not supporting it? Is because the bromine, the leaving group, and the hydrogen are not at 180-degree angle. Now, do you have to do that every single time? Probably not. Does it mean that this compound will never have elimination? Probably not. Why? Because this is a secondary halide. Okay, with a secondary halide and a base, you can also get a carbocation. Okay, so maybe it's not an E2 mechanism, maybe it's an E1 mechanism. All right, so other things are also possible with it, but an E2 will not happen, okay, with this one. So you can still have E1, and when you have E1, other things will also happen, which we will talk about in a minute or two, okay? Because remember, when you have carbocations, you have other problems as well. Okay, all right, so let's move on. So here I've given you two examples for the stereoselectivity, because not for E1, right? E1 doesn't have this. So in the E2 mechanism, the stereoselectivity I've given you is for when you have a cis versus when you have trans, okay? So hopefully this mechanism helps you. There's only so much space I can have on a slide. So I've tried to draw everything out as much as I could with the key points, okay, for you. So first of all, this is an equivalent symbol. And so you'd convert this into a chair conformation. There is no way you can look at this and figure out what's going on. And if you do that, it means you did not do all the work. And when I give you stereochemistry over here, it means that I would like you to go ahead and draw the chair conformation, because I want you to look at the the stereoselectivity of the leaving group. Now, if you take this and you choose to do an E1 mechanism, you can still get partial credit, because yeah, it's possible, okay, to have E1 also. But the fact that you have a cyclohexane and then you have the stereochemistry given to you, you have to understand that you need to draw the chair conformation, okay? Because even for an E1 mechanism, it's a good idea to go ahead and draw this and see if there is any steric hindrance going on or anything like that, because that's the one reason why you would get E1 versus E2, okay? Because in E2 mechanism, remember, everything is happening at the same time. We talked about the T-butoxide thing before. Is there are steric hindrance issues when you have bulky bases. So what kind of a base do you have? If it's a small base, then steric hindrance is not an issue, which means that you need to look at the chair conformation. That's what I'm trying to promote here, is for you to look at the chair conformation. Okay, so chair conformation here. Bromine goes on the top over here. I always put that as axial. Once that is located, then I'm going to go ahead and put my CH3, and which CH3 is going up here. So once that is fixed, then I will go ahead and pick out my protons that are anti-periplanar, which are these two protons as I showed in the previous slide also. So the base is picking up this proton, or it can pick up that proton, and then you end up getting two products from here. One elimination is going to happen on this bond, and the other elimination is going to happen on this bond. So then you convert it back into the proper cyclohexane that visually for us is a little easier on the eyes. And so once you do that, then you can see your Zaitsev product and Hoffman product a lot clearer. I mean, you can see that here also, okay? But it's a lot clearer like this. So once you know that, then you label them as the major and the minor and Hoffman and Zaitsev. Just labeling it as Zaitsev doesn't help because sometimes maybe that's not the major product, okay? So write the major also, and also that it's a Zaitsev product. So now this one here is for the trans relationship. So again, Br is on the top over here. And now the CH3, because it's trans, is going to go opposite direction. So which is going down now. Okay, so this is axial up, this is axial down. So which means this proton now is actually equatorial. All right, so this is not axial, which means there is only one hydrogen available. All right, for elimination. And that gives you this, which means you only have the Hoffman product. You don't have a Zaitsev's product in this case. So, which means that if you want to make a Hoffman product, then start with this kind of a substrate, right? And you will end up getting a Hoffman product. So all of these mechanisms, all of these things, they just tell us how to make the product we want to make, okay? Because that's the whole point of doing synthesis, except when you're just exploring, right? Which is also something that you do, right? Yeah. So now with E1 mechanism, what's the issue with E1? And the E1 issue is the rearrangement. So we've talked about that before for SN1 also, because in SN1 also you're forming a carbocation. As soon as you have carbocation, you start having rearrangement problems. So the same thing is going to happen here as well. Okay, so nothing is stopping it from happening here. So here is a substrate. Bromine leaves, okay, as bromide. Once it's gone and you form a carbocation, again you look around to see if anything is, shiftable, or okay, that sounds very shifty, movable. So if you can transfer something, so here we can do a hydride shift. Once you move the hydrogen and then you have your carbocation here, okay, on this carbon, which is a lot more stable than secondary. So this is a tertiary carbocation. Once you've done the shift, now you look for the 3 protons that can be eliminated. By the way, you might remember from SN1 that if it is possible to form a more stable carbocation, you will form it. Okay, so which means you do not do any eliminations on this carbocation. Once you've done the shifting, that's when you do the elimination. Okay, so no products from here. All right, only after rearrangement. So once you've identified your 3 protons, I haven't shown the arrows here because it will get too messy. I mean, I can draw them right now, just for one if you want me to, just draw it out. But this is kind of what it means, right? So this is what you're doing, picking up a proton. Proton is leaving with its electron. So that's kind of what the arrows would be. But anyhow, so you end up getting 3 products because you have 3 protons to eliminate. So now when you look at the products that you have, you can see that this is substituted, this is not substituted, this is substituted. Now the substitution between this one and this one is almost equal. So these are going to be your major products, and then the minor product is number 2 proton, or whatever. Anyway, so that will give you the minor product. So in this case, you end up getting 3 products, okay, in which case you have 2 products that are almost equal in quantity. Now, will you do this reaction? Practically speaking, in a lab is probably not a good idea, because why would you want to get 3 products? But you choose your substrate carefully then, right? Because if you choose a substrate like that, then you should also know that you're going to get more than 1 product, which means you're going to lose some of your product, okay? That you may want only one of these products, you may not want all of them, okay? So, again, we learn all of these things to make our life easier in the lab, so that way, when we are ready to work, then we choose the right kind of substrate, and we end up getting the right kind of product. But rearrangement is possible in case of E1 mechanisms. Here I've given you one more example of a rearrangement, but in this rearrangement I also gave you a ring size change, okay, just so that you can see how the rearrangement can happen, and the ring size can also change, okay, with that. So for example, here, this is the substrate, the chloride leaves, and once it leaves, then you have this carbocation. Now, in this case, the carbocation is secondary, so you can do a hydride shift and get a tertiary carbocation. Again, you will only, get products from the tertiary carbocation, not from this one, okay? Unless I give you products and then I say predict what happens, and even then, usually, you're going to have to shift, okay? But in some cases it may not be. But anyway, I give you a lot of substitution and elimination products for questions. But anyhow, back to this, okay? So again, there are too many arrows here, and I didn't even color code them this time. I'm like, I think you guys are all pretty good with what's going on here. So the chloride is picking up proton number 1 here, chloride is picking up proton number 2. These are both the beta protons, and then here are the two products you will form. Now both of them are pretty good as far as the stability is concerned, because they're both internal. So I would say that both of them are going to be equal, okay, in quantity. Now, once you have this carbocation right over here, so I've drawn that out here without the hydrogen, because instead of moving the hydrogen now, I'm going to go ahead and move this bond. Once I move this bond over here, this is the product I will get. And if it is not clear to you, let me go ahead and just draw the skeleton. So here is what we end up getting, right? So this has moved. This bond has moved here, so which means you still have this, and now the carbocation is going to be tertiary. Okay, so that's kind of what happens with the shifting here. So again, you're leading to something more stable. If it was not going to be more stable, then there's no need for any kind of rearrangement, all right? But the whole point is that you are getting something more stable. Okay, so once you have done the rearrangement, and here it is, and now you have a beta proton, on this carbon, and then another one on this carbon. So here now we are going to get two products. And in these two products, one definitely is the Hoffman. This is the terminal alkene, and then the internal one is the Zaitsev. So that's going to be your major product that you have. So are you going to get all of these four products? I hope not, my goodness, but I think you will, okay? Because there is nothing stopping the rearrangement to go from here or here, because both are leading to a tertiary carbocation. So because of that, both of these rearrangements are possible. So because of that, you may actually end up getting four products. Yeah, have fun cleaning that up, right? So anyhow, that's that. Moving along. Dehydration of alcohols. This is an elimination reaction also, and this is always going to be E1. Okay, it's very rarely going to be E2, although I will mention it to you about the E2 as well. But most of the dehydration of alcohols is going to be E1. Okay, so how is that working? Let me just show you. So here's an alcohol. Now, alcohol, if you remember, we've talked about the OH group as being a terrible leaving group. Okay, we said that OH minus is a strong base. It doesn't leave. So, but we did learn how to convert it into a good leaving group by treating it with an acid. Okay, that's exactly what's going on here. So you take the leaving group, which is not good, make it into a good leaving group, and then if you're doing elimination, this will also work. Okay, so dehydration of alcohols to get alkene is a very good way of making an alkene without having the doubt of what's going to happen. Okay, so but I mean, with E1 you have issues. I mean, you still have the rearrangement issues, you still have the major minor problems, right? Those are also going to be there, the Hoffman and the Zaitsev. But otherwise, the mechanism is clear cut for this, and you can start with the substrate that you're sure about to give you the product that you need. Okay. All right, first of all, let's talk about the different kinds of alcohols. So there are three kinds of alcohols: primary, secondary, and tertiary. Just like you have a primary halide, secondary and tertiary halides, similarly you have these different kinds of alcohols: primary, secondary, tertiary. Now I want you to look at the products. They're all alkenes. Okay, so we are still getting dehydration here, so that's not a problem. I want you to focus now on these acids that we are using. Look at the primary acid. The acid needed to dehydrate primary alcohols is concentrated sulfuric acid, which really is very concentrated, very dangerous to work with. And then you're heating it as well. You know, I mean, that's a lot. For secondary, you're just using concentrated sulfuric acid and you're getting the alkene. And then look at the tertiary. You just need dilute sulfuric acid. You don't even need to do much more, okay, with that. It means what it tells you is that the tertiary alcohols are the easiest to dehydrate, okay? What I'm telling you is how do you decide your synthesis also, right? You're not going to use a primary alcohol for dehydration because obviously that's a killer. You know, this is very harsh conditions. So tertiary alcohols will dehydrate easily, okay, from here. The thing about the tertiary alcohol, as you're thinking about, you know, your mechanism of the reaction, which here, I mean, it clearly says E1, it tells you then that it is a carbocation mechanism, because a primary alcohol will not give you a primary carbocation, and that's why this is a very harsh condition. Tertiary alcohol, on the other hand, as you follow the E1 mechanism, it will give you a tertiary carbocation, which is very stable, easy to form. So the conditions are also very tame, okay, for this. So, you know, just the fact that you already know that tertiary carbocations are more stable tells you that this is very favorable. And then now the conditions are also telling you that this is favorable. And now you're also certain that this is E1 mechanism because, yeah, this is going to be forming a tertiary carbocation. So here are the different cations that can form primary, secondary, and tertiary. Okay, so again, the way the mechanism is going to work for us is going to be that the OH is going to get protonated, make it water, okay, which is going to be H2O plus. That is how it's going to form. Then it's going to leave, and then we'll have the elimination. Okay, now the problem again with carbocations is you can have rearrangements. Okay, and that's of course is more for secondary, not for tertiary. Tertiary is already stable, so if you're going to form, you know, a primary or a secondary, you know, primary was probably not going to form. Okay, but in some cases, as I'll show you, okay, you can have that as well. So then in secondary, for sure, you have to watch out for rearrangements. Okay, so all the issues back on the table. So here's an E1 mechanism, just a general mechanism. You can read this on your own. Right now, I'm just going to explain everything to you. So here is the alcohol picking up a proton from sulfuric acid. This is your very generic mechanism, okay? Then you get the protonated oxygen. Remember, this was called the oxonium ion. So once you have that, this is going to go away as water. Once that leaves, you form a carbocation, okay? And then the HSO4, which is, or it's 4 minus, which is the conjugate base of sulfuric acid, will come in and pick up a proton. You can also have water picking up a proton. Do not have anything else there. Okay, remember I've talked about this before. In any kind of a reaction, you can only use what I give you or what you form as a side product. But you can't use anything, you know, of your own. So here the conjugate base will then pick up a proton, give you an alkene, and of course I can see that I don't have the alkene, which I will draw in the PowerPoint, but right now here it is. Okay, so you end up getting an alkene there. So this is your traditional mechanism for any kind of dehydration. All right, so you have to show all of these steps in order to get credit. Okay, so here again is a mechanism E1 with rearrangement. Now we've done this before. This is nothing new to you. The only thing that's new is now we are using alcohol instead of a halide. Okay, so even if you flick back a few slides, you will see that I gave you rearrangements with halide. So in the case of halide, the halide was leaving first and then the base came in. Here the halide is not there, so you have alcohol, and so you first have to convert that into a leaving group, which once that leaves and you get a carbocation, then everything is fine. Okay, and of course then the conjugate base will pick up a proton and then give you the products. Okay, so the difference here with the alcohols generally is that your substrate is going to be starting the reaction, okay, and then getting protonated, and then the water leaves, you know, so you have to show all of these things, okay, in with alcohol substrates. Just a little bit about the dehydration of primary alcohols. Okay, first of all, you don't want to do dehydration of primary alcohols, but if you do, it's going to be more of an E2 kind of a mechanism, because you're not going to form a primary carbocation. Okay, so once you've done the protonation of the alcohol, then the second step here is just to pick up a proton. Everything happens at the same time, and so then you end up forming an alkene. Now, if you see this, I took a very small alkane over here, only 2 carbons. In the next slide, I have more, but you know, right now, in this case, there is no other mechanism possible. This is it, okay? But then you remember what harsh conditions we would have to use. So, you know, find something else, okay, to make this alkene. Don't use dehydration to make the ethene. So here is another one where you can actually use primary alcohol, but now this one will be via E1. Okay, how is it E1? So in this case, once you do the protonation and then this is gone, then you form a carbocation. Now this actually will not form because, and I didn't write it over here because I said I will explain it to you, and I may write it separately out, but generally these kind of steps happen at the same time because primary carbocations are not very stable. So whether you write it as, you know, 1 step or 2 steps, it doesn't really matter to me, provided you make sure that you convert it into a secondary carbocation. Okay, so make sure you do that, and then once you have that, then secondary carbocations will then undergo dehydrations to give the alkene. That's not a problem, and in this case you will get only the 1 alkene because there is only 1 proton. Okay, so primary alcohols, first of all, you don't want to start with them, but if you do, and if you do have more carbons, unlike the previous slide, then you can get rearrangements in there. Okay, so would you get 1 butene in there? And you know, here, no, never. Okay, because the primary carbocation is not stable. It will not stay. It will convert immediately into a secondary carbocation. Okay, so keep that in mind. Here is a problem for dehydration of alcohols, and you can go ahead and check this out. I mean, after we've done so many eliminations, these ones should be easy to follow, okay? But then again, I'm here if you need anything. So here's a little bit of a review. I can't believe we're almost done with this. So review for synthesis of alkenes. Now this is synthesis of alkenes, okay, because it is an elimination reaction, but really what you're doing is you're making an alkene, okay, in the products. So there are 2 eliminations that we've learned so far, which is the dehydrohalogenation, which is minus HX, okay, minus HX meaning that you have an alkyl halide as a substrate. Okay, when you have alkyl halide as a substrate, then your leaving group will be HX. When you have alcohol as your substrate, so alcohol substrate will give you minus H2O, right? That's how it is. So that's what this means over here. So you learned about 2 different kinds of substrates to do eliminations. Then we also talked about the Hoffman product, or the Zaitsev product, and the Hoffman product. Okay, now the non-Zaitsevs, I mean, you don't want to say that. That's why I say, you know, Hoffman product is, you know, a better way to say it. So Zaitsev's product and Hoffman, remember, Zaitsev's is more stable alkene. And then of course we talked about the antiperiplanar. So this is going to be only for E2. Okay, this is not for E1. E1 doesn't care, antiperiplanar, because you have a carbocation which is planar, so boom, no problems over there. Okay, so when you have you know, E2 mechanism, then you have to worry about these things. for here somewhere you may want to write about elimination here, that if you have bulky bases also, okay, so bulky bases will give you more of Hoffman product. Okay, so if you want to write that somewhere, you can do that too. And then of course if you have a carbocation, you're going to get rearrangement. There's nothing you can do about that. And here are your conditions for elimination. So you have two different kinds of elimination, E1, E2, first order, second order. So first order, of course, only dependent on substrate, tertiary carbocation. The base here does not need to be very strong, okay? Why? Because everything is not happening at the same time, which means it's not part of the rate determining step. So because it's not part of that rate determining step, the first transition state, it doesn't have to be strong. In E2, you need to have a strong base, okay? I have another PowerPoint in which I'm talking about all of these different conditions. So this is not the last one, okay? There is one more. I know you're probably thinking this chapter is never ending. It's ending soon, okay? So for E2, you need a strong base, okay, to form elimination products. What kind of solvent do you need? E1, E2, again here E1 you need a polar solvent. Here non-polar solvent will work as well. And then E1 competes with SN1. Okay, I've talked about that before. I gave you one slide in which I wrote out the SN1 product also. And that's because it's a common thing, okay, that if you're having if your mechanism is E1, then you might get some substitution product also, which means that unless you're doing a very clear-cut E1, which is like a dehydration, okay? Dehydration of alcohol will just give you dehydration of alcohol. But if alkyl halide is going to be your substrate, then you have to watch out for substitution reactions, okay? Just it's a drawback of E1. And E2 will compete with SN2. So again, how do you eliminate that competition is by using a strong base rather than a good nucleophile. Okay, so remember nucleophiles go for electrophiles. So you need a strong base, which means something that picks up a proton. So, I gave you some bases before, but one other thing that can help you with elimination, and I think I have that on the other PowerPoint, is heat. Okay, so if you add heat to the reaction, so you increase the temperature of the reaction, then you promote more elimination than substitution. Okay, so there are things you can control a little bit there. And then we talked about stereo chemistry over here, giving, Zaitsev's products and whatnot. So anyhow, these are just the conditions, these are mechanisms. We have to decide ultimately what substrate we want. We have to decide, is this reaction going to be good for us to give us the product we need or not eventually. So there was a lot here also for us to learn, a lot of new things, right? Zaitsev's, Hoffman, regioselectivity and whatnot. Rearrangements I know you had done before, so that was not something new, but some of the things were new for you, okay, in here. So again, remember, I have another PowerPoint for you in which I discuss all of these things and give you a little bit of a summary.